Hello everyone, my name is Andrea, and in this video we're going to explore two different functions of the Scipy package, which are UnivariateSpline and LSQUnivariateSpline. As you may guess, the central focus of these functions is the generation of splines. What are splines? Well, basically splines are mathematical functions that are used in different fields, but especially for fitting and interpolating given data points, the given set of data points. Um, well, splines are a really powerful tool and a really versatile tool both, because they allow for fitting and analyzing very complicated set of data points. Mm, I mean, they are defined as an ensemble of polynomial functions, which is, I would say, the main feature, one of the main features of spline functions. Since basically, as you can see here, I can just, so I've searched them on Wikipedia. This is a spline function here on the right, and as you can see, they are basically defined by different points, which are called the knots of the spline, and for each pair of knots we have a different polynomial equation that describes this part of the spline. As you may understand from this example, the one of the other main feature of the spline functions is their continuity. They are continuous over the whole range of knots that are defining the splines, which is very important since they allow us to obtain very smooth functions that can approximate our distribution of data points, our cloud of data points. The fact that they are defined, I mean that the polynomial functions that describe the spline are different for each, let's say, pair of nodes, provide splines with a great advantage compared to the polynomial with a standard polynomial fit, for example. And what is the reason for this? When we fit our data with a polynomial equation, we basically use the same equation to fit the whole range of data points. And this implies that basically when we have very complex functions or very complex distribution of data points, to try to find a polynomial function, a single polynomial equation, let's say, that correctly fit and follow our data points, we have to go with higher degree polynomials. And as you may see, I left in the article a YouTube link to a video which is very useful for understanding this topic. I really encourage you to have a look at it. I was saying that, yeah, when you go to higher degree polynomials, there's the risk that you're currently increasing the error in your approximation instead of decreasing it. So you may you may face some problematics trying to increase your degree, your polynomial degree in the seek of the better fit for your data points. Well, if you're using splines, you can basically change the polynomial equation when passing from a pair of nodes to the other, and so this allows you to have a very good fit while keeping low the degree of the polynomial equation that is fitting your data points. So this is the great advantage that Spline introduced to our fitting procedure. I think it's really remarkable. Just a brief note that I really appreciate about splines. They, from an historical point of view, you may not know that basically splines were firstly introduced by shipbuilders to design their vessels. Basically, since splines they were intended as very smooth piece of splines. Let's say that is the correct word, splines of metal, or wood that were used to design the vessels. And with very continuous and smooth functions, you can generate let's say harmonious shape that defines the vessels. If you want to know more about this this historical, let's say, background, just check on Wikipedia, and that's also on the website. So now that we have defined and that we have a little bit of knowledge about what are splines and what they are used to, let's dive into the code. So I've already saved my script, and we can just start by importing our usual packages. I will start by importing matplotlib, since sooner or later we will plot our data, plt. Then I will import numpy, and finally I will import the two functions that I will use throughout this video tutorial, let's say, which are part of the interpolate package of the Scipy library, and they are called in order UnivariateSpline and LSQUnivariateSpline. Not very common to be, not very handy to be written in this way, but yeah, there they are. Okay, perfect. So as in a lot of cases when we are just dealing with fitting problems, we have to first introduce and define our initial x and y arrays of data points, which we will use to try to fit them. So I will just define the x array with linspace as usual, and I will just start from 0, go to 10, and let's say 30 equally spaced intervals. Then I will define my y array, and for the y array I'm just choosing like a random function. So let's go with the sine function, like 0.5x, and let's multiply it for another sine function in which I will introduce some noise by using the random function of the numpy package, rand n, and I will give it 30 as the number of elements in the x-ray. Rand n is a function of the random is a part of the random function, which basically draws samples from a normal distribution. So I just did this part of the function just to introduce some random noise and variations to the normal sine function, which will be too easy to be fitted. So these are our x and y initial data points. Perfect. Now what we have to do, we basically have just to call the UnivariateSpline function, but before calling it I would like to explain a little bit more this function, because I mean it's really easy the application of this function is really easy, but it's not really easy to understand what the different input and the parameter that are really regulating the function of this, the function of this function, yeah, it's not easy to understand them. So I will basically explain them. Basically, let's see in the documentation what the UnivariateSpline function is. So the mandatory input of this function are the x and y array, and that's it basically. These are the only two mandatory inputs, which are our initial arrays of data points. I would say that, as you can see, the function has a lot, quite, yeah, different sorry, different input, optional input. I would say that the most important ones are k and s. K is the polynomial degree, which describes basically the degree of the polynomial function that will be used to generate the spline, and the default value is 3, if I'm not wrong. The other parameter, which is in my opinion even more important, is the smoothing factor. The smoothing factor basically regulates the error that the error limit that must be seek when creating the spline. And yeah, in the documentation of the function is defined with a very, I mean, it's not very immediate, this formula, but it basically tells us that the difference, as you can see here, is in the case that you apply a weight to the different nodes of the spline. But yeah, we are basically telling that the squared difference between the real value of the data point in that x point and the value of the spline on that x point is less than our smoothing factor. Another thing, so we basically set, I mean, by setting the smoothing factor, we basically establish the limit for the maximum, let's say, difference between the spline and the y data points. Another thing that has to be known is that by changing the smoothing factor, we are indirectly affecting the number of nodes of the spline. And this is very important because, I mean, if we, especially because spline functions are extremely sensitive, at least when we generate it with this UnivariateSpline function, they are really sensitive to changes in the smoothing factor. So we can change the number of nodes quite a lot by applying very small changes in the smoothing factor. So we must pay attention to this. But I will also show you a method for circumvent this problem. So now that I've introduced you to the function, we just have to use it. So I would just write the comment UnivariateSpline, not LSQ, UnivariateSpline. I will call the function spline. The output of this function is the function, is the spline function that approximates our data point. So we then have to apply this function to the new x array in order to obtain the y array containing the point along the splines. But yeah, it will be simpler than when I will just type the code. So let's go with UnivariateSpline, and as I said, the mandatory input, the x, the y. I will just keep with k, a default k value, so the degree of our polynomials will be 3, while I will define the smoothing factor s is equal to 5. Perfect. The next thing is to define a denser x array compared to the initial ones, because one of the main utilities of the splines is that they can also interpolate our values, and for interpolating we have to interpolate over a denser X-array compared to the previous one. Otherwise we will basically do nothing useful. And I will use again linspace from 0 again to 10, and this time instead of 30 I will ask for 1000 values. Perfect. And then I can define my y-array spline, in which I will store the y value along the spline that I've just created by calling the UnivariateSpline function. So the only input that I have to enter is the new X-array. Perfect. So we're basically done with this. I can just plot. So I will just write some plotting commands. Equals plt.figure. Okay. Ax equal vec.subplots. Perfect. And then I'll just begin by plot the initial values as a scatter plot here, and then I will just plot our spline, our spline function. So x spline, y spline, and I will give it a color. Sorry, let's go with the green. Okay, I can just show the ending result. Let's say there it is. Well, it's not very good actually, right? I mean, there's a lot of data points, and the spline function does not seem to follow them very accurately. And I mean, this was expected, at least by me, because our smoothing factor is really high, 5. So now the thing that I will do is try to correct this, and in order to improve the situation. In order to do that, I will not change, as I told you before, the smoothing factor directly, because in this way I will change the number of knots and the knots that I've just found. So to do that, I will just use a method that is called setSmoothingFactor, and this method basically allows for changing the smoothing factor without affecting the previously found knots of the spline. So I will just type here. Well, we can just cancel all this for the moment. Oh, I can just, I will just start here. So let's say set smoothing factor method. Okay, so what we're gonna do is simply apply this method to the spline function. So spline dot set smoothing factor, here it is, and we just have to type in what's the smoothing factor that we want to apply. I will go for 0.05 this time, which is really smaller than 5, so we should get definitely a better result. And then we have to create another spline function, of course. I will call y_spline2, and it's the same now, spline, and we will apply to this same X array, so X spline, and that's it. So now for the plotting, this is really the same. This is the same. I will just add some transparency here, because we will plot the old spline and the new one all together. Okay, I will just copy paste this for simplicity, and I will just change in spline 2 and the color to blue without the smoothing factor. Perfect. And I think we should be done. Let's check the result. Here it is. Of course, as every time I run the code, the random function will change. So the green function that we obtained now was different from the previous one. But here are, the same points for both the green and the blue ones in this time. And as you can see, by setting the new smoothing factor, it really improved the situation. As you can see, that the blue curve really follows accurately all the data points of our X-ray, and it's definitely better than the work done by the green curve. So yeah, once we know how to how to build a spline function, we can also apply there are a bunch of other useful methods that can be applied to the just created spline function, and I will just show you some of them, which I think could be really useful when dealing with a random set or specific set of data points. So the first method that I'm going to show you allows for, well, we can just avoid to plot every time the function. As I was saying, the first method will allow you to evaluate the value of a point on the spline on the spline, and it's very simple. I will just print it directly. The method is called _call, and the only input that we have to enter is the point in which that we are interested in. So if I'm not wrong, the X array goes from 0 to 10 approximately. I'm just interested in the value of the X number 2 point, and I should obtain his. Well, we can just plot the function in order to check whether it is accurate or not. The Y value on the spline for the point which X coordinate is equal to. Let's see. The point should be here more or less. So more or less here, 0.2025 more or less, I think. Let's see. Yeah, actually it was a big difference, but yeah, I think this is more accurate. So 0.47. Yeah, maybe it's better for the next to left the plotting command at the end, just to have the double check in the real time. So the next method that I'm going to present you is for obtaining the value of the residuals, which are evaluating basically the error between our approximation and the real value. They are really useful to be reported in order to show the accuracy of our fit, especially in scientific works. So I will just get the residuals, and the method is again really simple, so I'll just print it directly. Spline dot is simply get residual, and that's it. Let's see again. So the first here is the value of the number along in the vicinity of the number 2. We can check again for its accuracy. Let's see here. For example, yeah, it tells you 84, which should be, yeah, it's accurate. And then this is the residual. So it's 0.05, let's say, which is good for the value of the residual. I mean, the lower it is, the better. Another method that I'm going to show you again is how to obtain the integral of the spline, which basically describes the area underneath this, or better, not underneath, because our spline could be also lower, it could go lower than 0, but it's the area between the spline function and the x-axis. And we can basically so I will just comment. So it's from a mathematical point of view, we're just evaluating a definite integral of the spline. Again, really disappointing, this auto correction. Okay, print again spline dot, and the method is simply integral, and we have to define the initial and the final limit of our integration. I will just go, for example, with 1 and 2. I can just stop plotting because it doesn't have any relation with this, and I will just also comment the other two methods just define in order to get only this result, and we obtain basically the value of the integral between these 2 points of our spline. Okay, the last method that I'm going to show you, it allows for obtaining the roots of the spline, which are the points in which the spline crosses the x-axis. So again, I will define obtaining the roots of spline, and the method is really, again, very simple. Spline dot roots, and that's it. I will comment the previous one, and it returns you type it wrong. It returns the array containing all the x data points in which the spline crosses the x-axis. So that was it for UnivariateSpline function. Now we can just start if you're interested in the second part, which will describe another function, LSQUnivariateSpline, which allows you generating spline function with a slight difference from the first function that we have just explored in this initial part of the video. So yeah, if you are interested in that, please follow along. Okay, so let's begin with the second part. I will just cancel all this part. I will just keep the initial definition of the x and the y array, I think. And I can go further now. So as I was saying, this second function is the LSQUnivariateSpline. It's very similar to the UnivariateSpline function, but the main difference between the two is that this function allows creating a spline by directly controlling the number of nodes and their position. So as I told you before, when we were varying the smoothing factor or in the UnivariateSpline definition, we were indirectly changing the number of nodes of the spline, and we had to use the method set smoothing factor in order to leave constant the nodes that we have just found in the previous calling. This time, by using LSQUnivariateSpline, we can just we can just change and in the number and the position of the nodes and make our spline function varying based on this. So sometimes it might be more useful to use this function, because basically we could just be in a situation in which we want really to keep some points of our distribution invariant, and we want to force our spline to pass by those points, and then we can just define those points as the knots of the spline. So just to show you how this works, I will just go on and comment UnivariateSpline. Okay. I will just create two different arrays, one containing more points and one which is less dense, just to show you the difference of varying the number and the position of the knots on the creation of the spline. So I will just define this with linspace, and let me just define this, and then I will just explain you all the thing. T and T1 will be the less dense array, so numpy array, and I can initialize it as a list. Let's say 1.5, 0.5, 1, and 2.5. Okay. The LSQ UnivariateSpline function, as you can see in the documentation, accept as three mandatory inputs this time, which are the X and the Y array, but also the array containing the knots of the spline. Other optional arrays like that we saw before are, for example, the K, which is the degree of the polynomials in the smoothing splines, and the full value is 3. An important thing that has to be kept in mind is that the knots that we are entering in these arrays should be located within the range of the X value of the X array. So they have to be within the range of between 0 and 10. As you can see, I chose 0.1 and 9 as the two limits of my initial T array of 20 knots. And here, for example, I was really conservative. I was 0.5, 1, and 2.5. So this is the main thing to keep in mind, just not to get errors. And then we can basically go further and just call the function twice for the two different situations. So I will just spline and LSQ UnivariateSpline X, the Y array, the T, and let's just assign a degree higher than 3 just to show you how it looks like. I'll go with 4, and then I will call the other spline one LSQ UnivariateSpline X, Y, T1 this time, and equal to 4, because we want to have them with the right degree, with the same degree, and basically that's it. We can just plot very rapidly without too many things. X, Y, and I will go with the size, let's see, 8, just to be able to see the points. Dot plot, I will plot the first function. So I forgot, I think I deleted the denser X array. I will just write it again. Xspline equals numpy linspace, and it was like 0, 10, and if I remember correctly, it was 1000 values. Please forgive me if I just type it different from the initial one in the first function, but it should be this, and plot, and I can just create the Y array in the plotting command. So the X array is X spline, while the Y array will be the spline function applied to the X array. Perfect. I will go with green again. Well, wait. I mean, the green was the bad spline, so I think I will just invert, or just, yeah, I will just, the blue is the more correct spline. Let me just copy paste this. Okay, now we'll go with the one that is using the less dense number of nodes array, and I think we're done. Basically, I can just show. Oh, let me just, yeah, I think that this choice is a little bit unfortunate because the nodes here is very close to the initial point of the actual X array, so I will just convert it to 1, for example, just to improve the situation a little bit, because we could get very strange result. Let's see. Here it is. As you can see, the green one was the spline that was passing for, we forced it to pass for 0.5, which should be like here, I think. Here's the node. 1, which should be here, I think, or here. And 2.5, which is like, yeah, I think it's somewhere here. It should be here. And well, the other is passing for 1, 9, another 20 nodes in between. And as you can see, by increasing the number of nodes, we basically increase the accuracy of our spline in fitting our data points. So that was it. Well, another important point is that the methods that we saw for the previous functions are almost, I think all of the methods that I previously showed you are can be applied also to this LSQUnivariateSpline. So I will not repeat the same method also for this, because they are just identical and it's like very similar also the output. I will just conclude this video. I hope that it clarified a little bit to you what splines are and how we can use UnivariateSpline and LSQUnivariateSpline functions to build splines and to approximate our data points. And I would like to remind you that basically in the usual practice, when we are generating splines, a good procedure will be try to repeat the process to change the parameter of the splines, the nodes, or the smoothing factor in order to obtain the best approximation by using the lowest possible polynomial degree, and so but yeah, we have to introduce less error possibles by and keep our approximation as good as possible. So it's not easy. We have to make like a trade-off between increasing the degree of the polynomial function that we're using for defining the splines and the error between the spline and the actual data points. So yeah, usually what I would recommend you is to perform multiple iteration and see which set of parameters defines the best result. Okay, with this I will finish. See you in the next video, and thanks for watching. Bye.